And a very warm welcome back to FUSION24. If you could take your seats, please. So welcome back to FUSION24. Hello if you're just joining us online. Don't panic if you've missed any of the other sessions going on, because we are recording them and we'll be broadcasting the videos plus the slides on YouTube within the next couple of weeks. And you'll receive instructions by email on how you can view those. I've been given one very important announcement, and that is to remind you that there will be a drinks reception at 5:30. So please don't rush home. Please stay and continue to network and enjoy a drink with newfound friends and colleagues. In the previous session, we heard from investors about how, at least for some of them, the importance of commercialising technology along the way is important to them. And I'm delighted to say this is what this next session is all about, because fusion companies are starting to commercialise their enabling technologies, and they're already starting to find new markets for them. So it gives me just great pleasure to welcome onto stage our panellists, chaired by writer and broadcaster Stuart Clark.
Thank you so much, Valerie. It gives me so much pleasure to be back here again, 2 years after the last Fusion conference, I think. And I have spent an hour in the company of our panelists to talk about this fascinating subject in our preparation call. So I cannot wait to bring them up on stage so that you can hear some of these truly incredible things that lie on the horizon, not just for fusion, but the unexpected benefits and the technology that will spin out of that. So if I can invite them up one by one, and it's, first of all, Greg Peifer from TAE Technologies. Warrick Matthews from Tokamak Energy. Elisabeth Siegel from TAE Technologies. And Markus Roth from Focused Energy. Now, the best thing about being on this panel is for 40 minutes we get to sit in nice chairs, which I've been eyeing up all morning. And I get an iPad because there is the opportunity for our online audience to submit questions. They will pop up on the iPad here. So online audience, go mad whenever you want. And in the room here as well, feel free. We'll ask for some questions later on. I want to kick this panel off, however, by turning everything on its head. And you usually wait until you're running out of time to do the quick fire round at the end. Here, we're going to do the quick fire round to start with, because I think the important thing to set the scene here is all four of you represent companies that take very different approaches into fusion. So briefly, tell me about your company and your approach to fusion, and we will start with you, Warrick.
Quick fire, right? Those who know me know I don't do quick fire very well, but let's have a go. So we're a fusion company at our heart. We have two key technologies: spherical tokamak, HTS magnets. We'll go on talk more about HTS magnets. But we're in our 15th year. We were originally a spin-out from UK AEA. We've now grown to around 250 people, more than 60 PhDs in our company, specialists who come from around the world to work for us because we do things. So we have a track record of designing, building, operating, maintaining, upgrading a fusion device, and that device has set records for triple product and has achieved
100 million degrees Celsius plasma ion temperature. So we know our stuff, and we're ready for the future.
Fantastic. Elisabeth, tell us about TAE Technologies.
Hello. So pleased to be here. Thank you for moderating as well, Stuart. TAE was founded back in 1998, so we're the oldest private fusion company. We're headquartered in California. We've built around 5 national lab scale machines so far to prove out our design concept, which so we're pursuing fusion in the form of an advanced beam-driven field reverse configuration, which needs a catchier name. Suggestions welcome. And we're also pursuing sort of the end goal of putting fusion power on the grid by the early 2030s using hydrogen boron fuel. We have around 600 people working at TAE now, and it's 200 of which are actually based here in the UK, out in the West Midlands, working on our spin-off company, which I'll talk about later, no spoilers. Yeah, we're thrilled that some of our enabling technologies that we've developed along the way have been able to spin out. But ultimately, our goal has been to to pursue this commercializable pathway that we've identified for bringing fusion power to the grid in the early 2030s. And we're also investor and investor validated in the sense that we've raised a little above 1.2 billion in capital toward that goal. So yeah, thank you.
Superb. Markus, Focused Energy.
Yeah, Focused Energy has been born in 21 as a US-German startup company located right now. We're locating in the Bay Area in California and in Darmstadt, Germany. Our focus is, and we heard this beautiful talk this morning from Tammy, laser fusion, laser-driven fusion. We take a slightly different approach than the National Ignition Facility by going for direct drive, omitting the whole realm, and directly irradiating the fusion capsule. But in contrast to the regular approach, we are approaching what we call the fast ignition approach, where we basically separate the compression and the heating, because that is way more efficient, because as we all know, the kinetic energy, if you do a slower compression, you can compress way more mass, and that gives you a higher yield. And so we have looked for the last 30 years into all of these components on laser fusion to see where are the efficiencies, and that's basically our current approach.
Superb. And finally, it's Greg and Shine Technologies.
Yeah, thanks. Our approach to fusion is a little bit different, I think, than most companies. I think that we've heard a lot about seeking Q greater than 1, Q of 10, Q of 40, Q of 100. We kind of have approached it from what I'll call Q sub-economic. Our goal with fusion was to find a way to make money, frankly, with fusion right away. So we focused on applications where we could sell fusion reactions for more than we could sell energy. And just to put it in context, you can sell energy for something like 5 cents per kilowatt hour once you're generating electricity. You can sell neutrons from fusion reactions for something like $100,000 per kilowatt hour if you're applying it to certain markets. So we looked at technology that we could commercialize very quickly and get to market. And frankly, our strategy is to practice fusion and over time establish supply chains and lower cost. And by doing that, we think we can access subsequently larger markets as we reduce the cost barrier.
Fascinating. So you mentioned the technologies that could be commercialized. We're going to go down the panel once again, and this time break it down for us. What are the technologies within your company that you feel are commercializable, if that's a word? Warrick.
Me first? Yeah. So definitely commercializable. In fact, I'll say first, we're very pleased to launch a brand within Tokamak Energy, TAE Magnetics. And Liam Brennan here runs that business and is in the crowd. I can see him. Harriet Allen, business development. And that reflects what we're doing to really go after high temperature superconducting magnet applications. Now, we talked a bit about what is an HTS and why is our technology special in the prep call. And so we partner with companies to buy HTS tape. And excuses for people who are really familiar in the detail, but I'll break that down per your request. If you had an HTS tape, it would look like about a 12 millimeter wide ribbon. If you turn it on its cross section, it's about 70 micron thick. But only 1 to 3 micron of that is a superconductor. For us, it's REBCO, rare earth barium copper oxide. And we wind this into powerful magnetic field coils, because the amazing thing about the tape alone is that when you take it down to an operating temperature, it has 0 electrical resistance. So you can put thousands, millions of amps of current through it, and it doesn't even feel it. And for us, that allows us to generate coil packs and generate very, very high magnetic fields. You could say anybody could do that, buy some tape, wind it into a coil, put some power into it. What's so special? Well, we've been doing this for about 10 years. We have over 200 patents. We've got over 50 inventions. We've sunk about $60 million into that process so far. And we can generate very high field, but very robust, protected, unquenchable magnets. And a quench is when you lose the superconductivity. You've got all this energy that has to disperse, and very often you'll destroy the magnet. We have special technology that protects against that happening. High field, 24 Tesla plus. 24 Tesla is not a Californian parking lot. It is a measure of magnetic field. And if you express that as pressure, the best description I've heard is from one of those amazing PhDs, Greg Brittles in our company, who said, well, if that was a pressure, it would be like being at the bottom of the ocean, but twice the depth of the Mariana Trench. So imagine yourself at 20 kilometers down. That's the equivalent pressure. And we need that to compress and confine plasma. But when you look at other markets and say, what could you do with that field? If you're a market that's used to a permanent magnet that can give you 2 Tesla, and we come along with 20, it can transform markets. And we're starting to see that now. We are opening up market applications in this technology we're developing for tomorrow. We're commercializing it today. We're active already. I'm really pleased that we're partnering with other fusion companies. We want to do that. We can help accelerate their fusion mission by partnering with them. We are in the field of physical science applications, defense applications, and we're starting to talk with really big strategic opportunities. Like, think about...
Let's stop you there, because don't put all your cards on the table just now.
All right.
Look,
and it was the quick fire round, wasn't it?
Yeah. You've got them hanging, you see, so don't lose them now. It was cliffhanger. We'll come back to these. Elisabeth, tell me about the technologies that you're seeing that you can spin out, but don't tell us what the applications are yet.
All right. Okay. We'll try to keep from saying too much here. So there's two, I think that so far there's 2 core technologies to our fusion devices that we have spun out. So TAE Life Sciences is our spin out that uses one of these. So just to rewind a bit, I mentioned that we're pursuing fusion through a field reverse configuration. Our specific design for that marries the kind of insights of plasma physics as well as accelerator physics. And one of those, the kind of key ingredients, I suppose, to that the device design are neutral beam injectors. And something that we found along the way was that for this existing medical application, it's very difficult not to talk about applications, actually. So I'll get into more details later, but it's for cancer treatments, actually. And so we found out that this existing thing called boron neutron capture therapy that's known about and is available in Japan as a treatment and is in entering into clinical trials elsewhere. We can sort of pair a pharmaceutical agent and tag tumor cells, especially in sort of hard to operate cases, cancers of the head and neck, for example. We tag them with a boron compound. And then in 1 to 2 outpatient settings, we're able to use a modified version of that neutral beam that I just mentioned as being core to our fusion devices to target those cells and essentially melt the tumor cells while leaving the healthy cells intact. And it's a really great example of sort of the kind of like unexpected benefits that can come out from pursuing specific fusion technologies. And I can talk more about that in a bit. The other technology that I'll cover is spun out into TAE power solutions. And something that we ran into when we were designing our fusion devices, and we run hundreds and hundreds of experiments off our grid feed in Southern California, where we have our 5th generation device and are currently breaking ground on our 6th generation, which will validate sort of the net energy milestone by around 2026. Over there, we get, not very much from the grid. And we need around 2 gigawatts, I think, to turn on the machine, or 250, something like that. And the numbers escape me right now, but just to say, we need a lot of energy to turn on that device and start generating plasma for experiments. And we do that hundreds of times, and so if we could just do that, we would black out all of LA, very unpopular to do that. So instead of doing that, we found a way where we could create this hardware-software suite that goes essentially a cap that you put on batteries, and create these kind of stationary storage units that over time would siphon power from the grid, store it, and then be able to reroute it very quickly to wherever we need to turn on the fusion machine. And then we said, hey, that actually has a lot of potential commercial applications across a very wide range of uses, because it's the exact same thing that happens when you push down the pedal of an electric vehicle, for example. You need all that power in one place. And so we developed this technology that also improves battery life by about 20%, includes other performance metrics of the battery, and also it enables a lot of stuff to be done on that normal sort of standard grid feed, such as pulse power charging, like super fast charging, et cetera. So that's another sort of business then that has spun off and is working on a lot of sort of near-term, sort of ready-for-market applications right now.
Fantastic. We'll get into some more details later, but Markus, tell us about your technologies.
Let me answer that question in basically two ways. First, if I look at the subtitle of this panel, New Markets Created by Fusion. A lot of people think that the 20th century was the century of the atom with the atomic bomb. It is more likely the century where internet started. But the 21st century will be likely the century of the photon. With respect to the industry, but also with respect to new technologies like 3D printing, rapid prototyping, everything, ASML, everything that evolves now, controlled photons and plasmas. Now, with fusion in hand, this can create an entirely new market. Because if laser fusion comes into power, that means that we have a boost in the entire optics industry with orders of magnitude larger than what we have now. And especially here in Europe, we're extremely good at that. And that is, I think, one of the new markets that we can create. But let's be a bit more specific what we at Focused Energy has as an early revenue or spin-off. As I said, we are dissecting or we are using our lasers in two ways. First, one laser to compress the material, and the second to ignite it. Now, for the second part, we use something we call the ultra-intense lasers, which are lasers that have such a power because we are focusing light in space and time, that if we hit a target with that laser beam, the light pressure, only the photons impacting on that surface, is about 500 gigabars. That is way beyond the capability of the center of the sun. And it accelerates all of those particles in that foil from 0 to a certain percentage of the speed of light within thousands of billions of a second over a distance. And this is our particle accelerator. A usual particle accelerator is hundreds of meters. Our particle accelerator is of order of hundreds of microns. And this is the difference. So we're building these ultra-compact particle accelerators as secondary sources for customers. And we can use electrons, protons, all kinds of ions, neutrons, and very, very hard X-rays. And especially also these X-rays, they come from a spot size, the size of human hair. And that gives you a spatial resolution that cannot be done with any other technology. And that is one of our early revenue paths.
Amazing. We've all heard of the Large Hadron Collider. I look forward to the minuscule Hadron Collider.
It will be 27 millimeters.
Greg, what about your technologies?
Yeah, and I appreciate the title of this, having the "un" in parentheses. Certainly, the benefits we're pursuing are very expected and by design. We're selling the fusion itself, so it's not really a spin-out. Our goal was actually to be able to sell fusion reactions so that we can practice building fusion machines at scale. And we've built many of them, actually, and gotten quite a bit better at it over time. So we've started with what I'll call cold target technology. We've moved into what I'll call hot target technology, and are going to evolve. As the targets get hotter and hotter, the efficiency goes up and the cost comes down, but the level of technical sophistication gets higher and higher as well. So it was really important for us to find technologies that could operate with very high uptime, very high reliability to practice in commercial markets. It's essential for our path.
I understand. So we're going to go now to the actual applications, what you might be using this new technology to make possible or to enhance for us. And I'm aware that there may be some commercially sensitive information here, so I'm not asking you to give away any trade secrets or insider information. But Warrick, paint us a picture of the kind of applications that may be enhanced or become available for the first time.
Yeah, sure. So I mentioned where we are engaged already, and it's good that I was presenting at a panel, I think, at the beginning of this year, talking about the fact we'd got some money from a customer, and that was good news. And now we've got, I think, 23 commercial engagements on magnets. So we're really rolling. That does include fusion as companies, as I've mentioned. It does include physical sciences, where you've got advanced spectroscopy devices you can achieve with very powerful magnetic fields. Defense applications, sometimes that divides the crowd, but there is you could Google it, a DARPA pump program that we're engaged in. And that is a real-world Hunt for Red October marine propulsion system using magnetic field. And actually, I believe that will have benefits to decarbonize commercial shipping in the future, because you're going to achieve something that is more efficient than a propeller. Then we go into different realms where we're engaged with partner companies and we're discovering lots. I come back to, if you're used to a 2 Tesla permanent magnet and we can give you 20 plus, what can you do with that? And industries are becoming aware. They're approaching us, and then we're taking a business development approach. But for example, you can separate minerals with very strong magnetic fields. You can melt metals with induction heating. You can even separate impurities from molten metals with very high magnetic fields. You go into the world that we've heard of here a little as well, with proton beam therapy, hadron beam therapy, where you're killing cancers with magnetic fields. So we're really opening up the art of the possible. I mentioned wind turbines earlier, and that's just a great fit for high temperature superconductors. And maybe the power transmission from that wind turbine is another great fit, because it's a huge challenge that grids have now. How do you transmit power without the losses of the current state? In a wind turbine, you've got hundreds of tons of permanent magnet in the biggest ones. So if we replace that with a HTS system, you can use a tiny fraction of the rare earth. You can make it lighter. You can make it more powerful, higher power output. And these are the ideas that we're now exploring with the longer-term strategics, as well as driving the near-term value, because we want to get traction and momentum, open up the market, and it's also important to our investors, which we might come on to.
Yes, indeed. Elisabeth, you've mentioned the kind of medical applications.
Right.
So please feel free to go into more details there, or tell us more about the power system applications.
Yeah, absolutely. So I'll speak briefly on the medical side, because I kind of covered the extent. I mean, cancer treatment is really groundbreaking, and so we're trying to I think the difference here is to note that we did not invent boron neutron capture therapy, but given the level of precision, the level of science that went into, and R&D that went into developing the neutral beam injectors for our devices, in the sense that we had to sort of almost reinvent the wheel in terms of making them as precise and as we needed. That's been the difference, where now we're realizing that our whereas before BNCT was made possible with the precision of maybe like a sledgehammer, now we're doing the laser scalpel, right? Like so that's where the real value add comes from our technologies, and where we're contributing there. And so TAE Life Sciences, which was actually spun out back in 2017, is working on both the machine side of that that therapy provision, as well as the pharmaceutical agent that binds to the tumors. And in this way, it's a good option that we want to bring to more and more patients worldwide, because especially for those, again, with more inoperable cases, or where other sort of interventions haven't worked out, this is still an option to definitely try. And then also, it can be administered in a 1 to 2 setting, sort of 1 to 2 sittings in an outpatient setting. And so in sort of contrast to chemotherapy or other sort of longer term and more and sort of treatments that are a bit harder sort of on the patient, we want this to we see definitely a potential for this to bring sort of better outcomes to a much many more people who are suffering today. So that's what I'll say on the medical side. Switching gears now a bit to the power solutions side, really the sky's the limit with the applications of this specific, because in the sense of the future is electric, right? The future is really looking at batteries and battery life and battery longevity as solving a lot of various problems, including, so the applications of this both can go to stationary, that's stationary storage modules are sort of what we are working on sort of in the ready for market realm right now. And then in the near to medium term, we're also looking at applications in e-mobility, where we can help cars go much longer on one charge. We can help with the sort of current state of sort of batteries in cars and how they currently, operate off of the lowest common denominator of cell performance. And we want to, our technology can help with load balancing, can help with fast charging. And so it really is a versatile technology. Just to give you an example, so last week we announced a MOU that we signed with Occidental Petroleum, specifically with their direct air capture technology through Oxy Low Carbon Ventures. And so that's a commitment both to using and deploying TAE Power Solutions technologies, starting to work with them this year on that, in order to, because currently they take a very low to zero emissions approach to their DAC facilities, or their direct air capture facilities, and so this complements that approach very well, because we can engage with a wide variety of renewable sources and help them maintain flexibility and responsiveness with their energy needs in the near term. And then in the long term, there's also this tie back into fusion energy, because there's this commitment to exploring with us the use of fusion as a source of industrial heat for direct air capture. So it shows both the kind of the really complementarity of fusion with other renewables and other green tech, as well as it shows the kind of way that this pathway has kept us, on track for that ultimate fusion goal, but also has brought so many great sort of outcomes in the near term.
Fantastic. Markus.
So why should a fusion company focus on these earlier revenues or alternate solutions? And in my mind, it is very important not to be distracted from your main mission, fusion, because that's finally where you get all the world experts to work for. So in our case, we have decided to go for these secondary sources for 3 reasons. First of all, we have to demonstrate, if we ever want to build a reliable fusion power plant, that these lasers are not, the toy things where you need 100 of students running around and adjusting optics all the time, but these are industrial product working 24/7. And these secondary source drive lasers are exactly the first step towards that direction. Second, we need to increase the ecosystem. We need to strengthen the supply lines. If we ever want to build a power plant, and you have heard from Tammy, when NIF and LMJ was built, there were factories built making laser glass. These factories do no longer exist. We need to reestablish these supply lines. And for industry, they need an incentive. And the incentive is not, in 15 years we are building power plants. This is not how they invest today. They also need a path with milestones where they see that they have a growing business. And the third is we are developing these ultra-bright radiation sources. And this is exactly what we also need in our experiments in order to see what's going on the micron scale within the sub-nanosecond time scale. And for that, we have developed these secondary sources, and I don't want to go too much into electrons and protons because a lot of people have talked about that. Let's focus on 3 particle sources that I think I'm extremely excited about. Extremely hard X-rays. Try to find a conventional X-ray tube above 300 keV. It's not going to happen. So if you want to do a radiograph of a 1 meter steel reinforced bridge pillar to see if the steel reinforcement is still steel or rust, good luck. The Japanese have tried that for an hour, it didn't work. And so if you have a source that can deliver from a human hair type source, 2.5, 3 MeV X-rays, and not a few of them, but a lot of them, you can make projection imaging, you can do high resolution radiographs of objects. Non-destructive testing is the key here. So that is the X-ray part. Then, already mentioned the neutron part. We are optimizing a laser-driven ion beam into a secondary target for fusion. If you take that target as a neutron production target, you can make directed neutron beams of outstanding quality, very high energy, and ultra-short pulse duration. And we have demonstrated that we can use that technology to remotely inspect nuclear waste barrels through 1 meter thick concrete and steel reinforcement and everything. And we have a customer already for that. So this is an early revenue where we have a customer and we're lining up with Germany's largest energy provider in order to work on that. And so this is the neutron part. And then the ultimate goal, still a bit in the future, if you want to do muon tomography, that is the ultimate goal, because with muons, people have tried to find hollow spaces in pyramids. They are highly penetrating. But if you look then how the flux of cosmic muons on our ground is right now, it's 1 per hand per second or so. And when they tried to find the molten core in Fukushima, it took them, I think, 6 months to get a picture. It was not too sharp because of the flux. With one single shot, we have demonstrated we can make 10,000 muons in a directed beam. If we ramp the rep rate of those lasers, we can scale down 9 months to a few minutes, and then you can do muon tomography of very dense object, cluster containers for waste fuels storage and things like that. And this is a new technology that serves so many needs of the society right now, and I think this market is just starting, and we're very happy to be on the forefront of those market development.
Fabulous. Now, Greg, it fascinates me, this concept of selling fusion reactions. So tell me, again, without any commercial sensitivity, about the kind of customers you have or are looking for and the kind of things they're using this for.
Yeah, great. I'm going to try and walk through 20 years of business plan in a couple minutes. So, if we look at the past, and we've been at this for a little while, we use fusion to make neutrons, essentially to replace reactor-based neutron sources for a couple of applications, primarily neutron radiography. So this was just mentioned. It's actually very useful for defense applications. It's actually required as more and more parts are made out of materials like carbon fiber. X-ray gets less and less sensitive. So turbine blades on F-35s need to be imaged, every single one of them, as you make them. Neutron imaging is the only way to get the resolution they need. So we're already replacing reactors in that field. Non-destructive testing is a growing market for neutrons, which is very exciting. And then rad hardness testing is the other area. And again, defense applications primarily. Our defense sector wants to make sure that our satellites and space-based defense systems will survive a nuclear first strike. Fission reactor neutrons don't work. They're actually trying to harden against fusion neutrons specifically. So that's a great growing market for us. So that's kind of behind us and growing. That's a profitable division of our company and doing very, very well. Where we're just getting into now is we actually had to reduce the cost. So I talk about this reducing the cost curve and increasing larger and larger markets over time. We had to reduce the cost of generating a neutron about 1,000-fold to access our next market, which is where we are today. And we're now able to make neutrons cheaply enough to produce radioisotopes. So instead of just using them to take pictures, we can actually change matter from low-value forms to what I'll call hypervaluable forms. And hypervaluable sounds a bit like an extreme word, but let me give you an example. So we can turn uranium that we buy for $6 a gram into an isotope called molybdenum-99, which is used for medicine that's worth about $150 million a gram. We can turn ytterbium-176 into lutetium-177, which is an isotope used for fighting cancer. It's worth about $1 billion per gram. So these are actually really hyper-valuable things, and they get us into what I call small-scale transmutation. So we're just entering that market now. We just announced our lutetium-177 product to the market a week ago. We've been selling it since April. But again, it's a similar story where we're kind of replacing old dated reactors that are maybe 50, 60 years old and going away with much cheaper technology, much more modern technology. In fact, we're, 11, 12 years into a project that's got 2 years left to produce the biggest isotope generating factory in the world. So that's kind of where we are now. Going forward, we want to extend that capability. So if we can scale fusion again and bring that cost down another material chunk, we can do what I'll call large-scale transmutation. That applies to recycling nuclear waste primarily. So if you look at the nuclear waste stream from fission power plants, the vast majority of it can be recycled and put back in the fission power plant as a source of energy. Plutonium should be burned. It's the best thing you can possibly do with it. But there's a handful of long-lived waste products that have no use that, frankly, we'd be better off destroying. So fusion neutrons through high-energy N2N, N3N reactions can actually break those back down into shorter-lived or stable isotopes. And I'll throw out there an example of iodine-129, which has a 10 million-plus year half-life. You can transmute it into iodine-128, which has a half-life of minutes. You hold it for a couple hours and it's gone. So that's kind of where we're going next. It turns out that systems like that look a bit like fusion power plants, but they don't need 5 nines reliability. They can be up 50% of the time. You don't yet need to be making money at 5 cents per kilowatt hour. You probably get paid 10 to 20 times as much still per reaction there. And we'll get a lot of practice building machines that look like fusion power plants. So maybe that's more than a couple minutes, but that's kind of our 20-year plan for fusion. And again, phase 1 commercial, phase 2 it's commercial and growing, and I think we'll be the first fusion company to profitable, which we expect next year.
Amazing. So we are starting, unbelievably, to run out of time. Are there any questions here in the audience? And online, of course, as well. Do send your questions in. Yes, there's a right down here in the second row.
Bit easier. So we heard a little bit about this from Greg, and a little bit more from, I think, it was, who was that? It was Markus, I think. Yeah. Your two companies have taken quite a different approach to that commercializable piece. So you've mentioned that with Focused Energy, you're still very much focused on the fusion power plant, and these are just sort of things you're doing along the way, whereas you're doing the things along the way on purpose, and maybe someday you'll get to fusion power. I'd like to hear a bit more from Warrick and Elisabeth on, with your spin-off technologies, where are you finding that balance between possibly losing focus on the original goal, which was a fusion power plant, and making sure that you're going to survive as a company along the way?
Shall I go?
Yeah, go ahead.
It's a good question. So I would say the majority of our people are still very much dedicated to fusion, and we're a fusion company. But we have changed our strategy somewhat to be not pretending that we can do everything ourselves. So we are the designer of fusion power plants, and we have specific technologies that we will bring into them, but we're deliberately building big consortia around us of very capable companies at our side to give us global scale. And we're then taking that into public-private partnerships. And there are some of those in the UK, US, and Japan, to name a few countries. So that's very much a more refined focus for fusion. But all of the magnetic fusion requires a supply chain to scale up, skills that don't exist today to be prevalent. And we can grow that in some of these other applications. So it is a virtuous thing for fusion to generate business applications that can help HTS manufacturers scale. And that's why we're doing it. So we see the two as very complementary.
Yeah, much the same, I think. So, we have TAE Power Solutions as this spin-off, but also TAE as the parent fusion company is the biggest customer of TAE Power Solutions units right now, right? So getting these spin-outs going and getting commercial traction for them is also fueling this virtuous cycle where then the core fusion business can really benefit from the ease of access to scaling the sort of manufacturing of power supplies, manufacturing of neutral beams, which we need for our device, and which we also think has commercial viability for other fusion devices as well. And not just we think, we know, because we've been having all those conversations. And so I think that the core vision, similarly, is still eyes on the prize, commercializing fusion power for the grid. And this is really just sort of like creating that runway for us to do that. So it's very, very much oriented towards the power plant commercialization goal.
Mm-hmm. Any other questions? Yes, on there.
Hi there, my name is Sarah Wilkin. I'm founder of Fly Green Alliance. On Thursday, I will be speaking at the World Nuclear Association Working Group representing aviation as an end user. So my question is probably to Elisabeth, but maybe Greg. My stats for Thursday, as the energy requirements for aviation will increase by at least a third by 2050. And between 34 to 70% of the fuels predicted to be used are SAF, eSAFs, renewable fuels, and electric fuels. Are you already engaging sectors such as aviation, which is not going away despite some of the predictions and degrowth, as was mentioned before? Have you started kind of longer term engaging with aviation? Greg, are you already imagining ways to leapfrog some of these technologies and to bring more abundance to e-fuels, for example?
Nice. So yeah, happy to take that question. And I think, so in general, we want, and TAE is sort of positioning itself to be this one-stop shop that is validated both by the kind of MOUs that I've just mentioned, as well as a lot of the strategic industrial partnerships that it's forging in order to be a one-stop shop for scalable and innovative clean energy solutions. That includes the kind of core fusion, proposition that I've just mentioned, as well as the spin-offs. And so the answer is yes. I can't speak to any specific engagement at this stage with aviation as a sector, but I would say that as far as also our technologies that are the spin-off technologies application to e-mobility as a whole, that's huge. Like that's a huge part of this, and I think that I don't see why aviation wouldn't be a logical extension of that. And so I think that that synergy exists for sure, and we'd like to explore that in the future.
Maybe just a quick comment for a country like the UK. I think aviation is not the elephant in the room. The elephant in the room is trade, and trade goes by shipping. And there are only 3 ways to power a ship: sails, nuclear reactors, or e-fuels. And if you look how many e-fuels you need for Northern Europe, that requires 500 fusion power plants only for Northern Europe, just for the e-fuels, to keep the world trade afloat.
Yeah, and maybe to add, I had a great stat a few years ago, which was if the Air France KLM fleet flew 100% SAF, it would consume the world's supply in 1 day. So, it's very easy to say aviation, that's SAF and hydrogen, so park that, it's easy. But how are you making the fuel? And that really is where fusion has to come in, as producing SAF, producing hydrogen at the point of use, so you don't have to transport it all over the world. Really relevant for ports around the world that ships come in, can pull sustainable ammonia or hydrogen to power them, and we really need that. It is probably the hardest thing to decarbonize aviation. It's got the hardest mission, especially long haul. But if it's shorter haul, I reckon there's a magnet that could help there as well with electrification.
Well, that sadly brings us to the end of our time, and it has been absolutely fascinating. Honestly, I could have spent the whole day talking to you about all of this. I think the take-home for me in the preparation of this panel and the delivery of it today is that where it seems very easy for us to believe that the world will stay the same when we have fusion power, it's just the way the energy is generated that will be different. What we're starting to see is that actually the kinds of technologies and the engineering challenges that are required to make fusion power a reality have the potential to change everything. That we will be in a completely different world for our technology and our applications. And that surely is another added impetus and huge communication point for the fusion industry going forwards. So I want to thank so much Warrick, Elisabeth, Markus, and Greg for being so clear and so just inspiring in your messages and your visions for what you're doing. Thank you.
Yeah.
And thank you, Stuart, for just being such a wonderful host. Before we thank our panel again, I'd just like to remind you that we're having a break and we're going to be back here at 4:15. Stay here if you want to learn about the progress we're making towards those all-important supply chains that Markus talked so eloquently about. While in the information stage, the theatre on level 2, we'll be looking at all the creative ways that fusion organisations are reaching out to new audiences. Please put your hands together again for Stuart Clark, Warrick Matthews, Elisabeth Siegel, Markus Roth and Greg Peifer.